Great. Welcome, everyone. This is the Computer Science Operating System Section 6. This is week number 8, and today is Wednesday, March 6th. All right, so thanks, everyone, for joining me at this time. If you could, as usual, do the private chat with your name and ID, that'll be great. The topic for this week or today is the memory management. So we'll do the worksheet and the lab today. And next week is our spring break. All right. So this we're exactly at halfway point. So hopefully you'll have a needed break from this class. Okay, so I'm sharing with you the Blackboard for this week. And as usual, there's the instructional material. There are 3 assignments. Here's the Zybook, and here's the main memory worksheet, and then here's the lab. So if you look at the instructional material section here, you have the worksheet here, and then here's the lab instruction, and then 2 codes. Okay, so what I'll do is I will do the worksheet, and then I'll do the lab. Okay. But before I start, is there any comments or questions you guys want to ask? Okay, I'll take that as nothing yet. But if you do, feel free to ask. And so if you click on this worksheet, you should get this one. So you get this one. Okay. There are 11 questions in here, so I will go over them, but I'm not going to use this one because this one is for you. I'm going to use the one with all the my notes on them. Okay. So let me bring that over here. Oh, before I start this, I want to just come here and show you that there's a chapter 9 edited edition of the PowerPoint. So if you click on that, you should see this one. I'm not going to use this PowerPoint too much, and I just wanted to show you that it is available, and there are some pictures in here that I copy paste on here, so I may refer to it, but I just wanted to call your attention that we do have one that is in sync with the worksheet. Okay. Anyway, so here are the questions that I'm going to go over and the answers. Maybe the first the question that these are the same questions that's on your worksheet. So, you know, just wanted to clarify and start off with the context. And so when we say, you know, what do we mean by main memory? We always mean the RAM, at least in this class for operating system. Some other context or some other courses may refer to main memory as a secondary storage like hard drive or whatever, but for let me get rid of this video here so I can have better bandwidth. Anyway, so that's what we mean. And, you know, just in case that anybody's wondering, why do we need to even talk about RAM in operating system class? What has RAM got to do with the operating system? Well, the reason why, let me just kind of put it here. Okay. Well, here is the list of 3 typical textbook answer why we study RAM in OS class. The first is we want to be able to run the program pretty quickly, because if we run it from the hard drive, it would take too long. Okay, so it is possible to run it off the hard drive or SSD, but that is not how we do things, nowadays. So that's probably the first reason. Another reason is we are running so many applications and programs. We wanted to run all of them pretty smoothly. And by being able to manage
ये भेज देना 6-6
so,
हाँ तो क्या होता है क्यों 6-6 क्यों हाँ तो 6-6 भेज देना 3-3 बोलो
so maybe somebody can mute.
चलो उसको बना के कल जुम्मे के दिन भेज देंगे
Okay, all right. So, we run so many applications, and by managing the RAM that those programs go into, they can run pretty smoothly. And then we wanted to, use those applications and store the data easily, and they can all be done primarily on the RAM. But I think the real reason, as I kind of alluded to here, maybe I'll just say the real reason, or the bottom line, is that we want to run many more applications than feasible. And so, in other words, most people will run maybe hundreds of programs as soon as they start up the computer, meaning, not necessarily user applications, but there are programs that needs to run. And so if none of us have large enough RAM to accommodate all of them. So we need to be able to manage them so that they can all run. But I think that would be the practical reason. So when we need to figure out how to manage this RAM, and immediately there are three challenges that we face, right? So the first challenge is the size. Most people RAM is limited. Typically, typical RAM that we have is maybe 32 gigabytes, maybe 64 gigabytes, but it is much less than. So let's see, where's the less than 1 terabyte or 2 terabytes that we have for this storage, right? So the RAM is limited. And like I alluded to in the first question, we don't have enough RAM to put all of the applications. The other challenge is the number of programs that we want to run. There's too many, right? And maybe it's not necessarily the number, but the size of the applications that we want to run. So they're sort of related. And this is not as much of an issue nowadays, but it used to be that the RAM was a little slow. And what we mean by the speed is the access in terms of the reading and writing, right? Because the only thing that RAM does is just to house the data, right? So it's not moving. What is moving is the program's ability to read the data as well as writing. So that's the speed. But this is, pretty fast nowadays. So it's not much of a factor nowadays as before. Okay? But it is still limiting it because depending on what you get, that might impact, what you do. Okay? So let's talk about the three types of the management for the RAM. Okay, there are many strategies that's out there, but these are the three main strategies that people either use or they would make a variation of this or a hybrid of this. Okay, so the first one is the CMA, or the contiguous memory allocation, And both the segmentation and paging are sort of development of this. And after looking at CMA, it's an improvement. So let's talk about one at a time. So here is a picture of those three things. As you can see, the contiguous or the CMA puts the process. Let me make this a little bit bigger. P1. So this is the RAM here, right? And these numbers don't mean a whole lot other than maybe the 0 is the beginning of the RAM available space, not counting the LOS portion of it. But anyway, so when P1 comes in, we'll put it here, and then P2 and P3 and so on and so forth. So it'll put the processes into the RAM one after another sequentially right next to one another butted, right? So that's the contiguous. And the paging is sort of look like this. And the segmentation looks sort of like this. They're all a little similar, but they use different schemes and different names. So you want to be able to talk intelligibly using the proper designated terms, okay? So let's talk about the first one. How does the CMA or contiguous memory allocation work? As I alluded here, when the maybe I'll just put it here. Let me kind of draw this here a little bit so you guys can see. Bring up my this over here and kind of like this, right? So if you're using a CMA, okay, and you're like over here, and so if here's the programs, right? And as they are being loaded onto the RAM, so let's say there's a program 1, program 2, program 3, a part of this will come here, right? So this is the logical address 0 and so on, the 64 gig or whatever, right? So maybe here is the OS and here's, so when P1 comes in, we'll just put it right here. When P2 comes in, we'll put it right here. So we'll go like that, okay? So that's doing it in a contiguous way. Now, when we look at these processes in the RAM, we will call this the beginning of that process. And then this will be the end of that process 1, right? But we have a special name for that. We'll call this address the base. Okay? And then here we'll call it the limit. Okay. So these are important because, not because of the names, but because we want to keep track of exactly where they start and where they end, right? But the concept is also important because we may want to use not so much a actual address, but based up on this base address. So if this address is 100 and you are accessing this particular address, let's say 101, let's say 110, we would say base plus whatever the change is, right? So 10 or something like that. So that concept is going to be helpful for us later on. But anyway, so these right here are the physical addresses, right? So here we have the physical address right here. And then here, although we could be referring to the physical address, a lot of times what we do is we use a logical address. So this, we can call that a 0, or we can call, whatever this here that we want to call them, or we can just, use a, in this case here, both the physical address and the logical address is the same, okay? But for this particular process, but we could call it a 0, or we could call it whatever we want. But, that's, we could have a different address system is all I'm saying. But if we do, okay, if we are using a a physical address as well as the logical address, then there could be a confusion, right? So what we need to do is to use what we call a address binding. Okay? An address binding means that we're binding our logical address with the physical address. So you can say, you know, we're binding the logical address to the physical address, or you can say, you know, physical to the logical, but you know, they're being like coordinated, right? And you may be asking, like, you know, is it really worth using the logical address? You'll find out that we will kind of have to use that. But anyway, so that's what address binding means, okay? And then, so now we already run into a little bit of problem here, because as soon as we introduce this logical address, we'll have to do some work, because your computer, or especially your CPU, doesn't do logical address. The only thing that it uses is the physical address. Therefore, we needed to revamp the entire architecture, and the logic or translator that translates from the logic address that we're using to the physical address. Because when we access the logical, the memory, the only address this understands is the physical address, right? So we used to use the CPU directly, the RAM using the physical address, but because we want to do all kinds of schemes to allow us to use RAM more efficiently, we are now using the logical address. Okay? So this is an overhead, but it is an overhead that is worth it. Okay? So, but anyway, number 6 is, you know, what is a swapping? Before we get to more details on the CMA, you know, this is maybe we should cover this question. But swapping means we're swapping something between the two. What we are swapping is the process. Okay, so this is a good picture that you could see. So here is the main memory, or the RAM, and here's the secondary memories, whether it is a hard drive or you know, solid state SSD or whatever. When you are running out of the space in main memory, then you will have to kind of push this out, but you don't want to delete it because you're not done with it yet. But you want to put more processes into the RAM, but you know, there may not be enough space, so it comes in, and instead of putting back into the you know, saying done, we may put it back into the secondary space only to bring it back, or we may swap what is running with what is not running back and forth. So that's what swapping is. We don't do this often nowadays, although we may have to do this when your CPU or the RAM is kind of like maxing out, because you don't want to freeze the system. You want to continuously run it. So that's one you know, instance where you need to do this. Another instance is, like I was saying, if you know, if you have more applications than your RAM has a space for, then you know, the user is clicking too many things, you know, too many tabs, too many applications, then you know, you may not be able to do it, but you're going to try to accommodate all of that by swapping between the RAM and the hard drive. But you know, this is a problem. So there are two problems with the swapping. One is it takes too long, right? If you're running the applications from the RAM, it's pretty fast. But if you're running the applications, you know, using the swap that uses the secondary memory, now here.
Oh, I didn't know that. इसने आज 6:30 का रखा. I was like 2.
Okay, thank you. You know, whenever you access the hard drive or SSD, that takes a longer time, right? So that's a problem, and people don't want to wait that long. So the magnitude between these two are, about 100, maybe 100 or more. So you want to avoid this, right? And the other thing is, not only does it take long, but also when you are swapping between the RAM and the secondary memory space, the process here, okay? So let me just kind of write it here instead of just talking. So when you have a RAM here, oops, let me just get it back. So here's the RAM, and here is the process one, and you want to put it into the solid state, right? Or maybe because there are too many. It's all packed, and so you want to swap in with PX here, put it in there, right? But anyway, when you put this P1 here, you can't just put one here and be done with it, because when you bring this back, it doesn't know what was I doing, right? Oh, what was P1 doing? So you want to know the state, right? And was it holding any data? And was there any resources that it was holding on to? What happened to them when you put it here? Well, were they let go? So there's some issues that kind of complicates. So in order to avoid this issue, you have to save a lot more than just a P1, like a log or the whole everything about it, right? Like a metadata about the process one. So it's not as clean. And so there are some challenges, with the swapping. And so, it gets a little tricky. But let's move on to talking about the threads here. So what are the three methods of selecting the memory space for the CMA? Now, CMA is the first of the three memory management strategy, but within the CMA, there are three different methods. Actually, there are more, but these are the three common ones, okay? So what's called, one is called a first fit, right? And the other one is called the best fit. And the third one is called worst fit. So let me kind of explain what I mean by that. So let me do a new one here. So when we have a processes here, right, that are coming in to the RAM. And let's say we have a RAM, 0 to 100 here. Okay? And let's say these guys, take maybe 20 units or 20 gig or whatever, right? So of space. And let's say this is 30 here, and then 15 here, and maybe P4, 40 here and stuff like that. So when P1 comes in, I have 100. So I'm just going to take from the beginning. There's a P1 with 20. And when P2 comes in, I'm going to give him a 30. Now this is at 50 now, right? So this is at 20. And then when P3 comes in, I have a space here. So I'm going to give him 15 that he's asking for. So here's a P3, here's a 15. So this is 65. And then when P4 comes in, it's asking for 40, and I have it, right? So I put it here. Well, can I put 40 here? I can't put it in, right? Because how much do I have here? I only have 35, right? So I have an issue. But anyway, the order in which that this is being put in is called the first fit. Okay? First fit. In other words, in the beginning, it doesn't really matter because there's enough space. But let's say, and then I just keep giving it, right? But if I do, let's say, well, let me just kind of go back here. So here's a 10. Here's, let's say, 30. Let me do it this way. So instead of this here, so after a while, when the process is running, so I'll have a block here, that's available 20, and I have a block here that's available for another 20, and I have a block here that's for, let's say, 40, and then I have a block here for another 20 and maybe 15, let's just say, right? So here's the available. So when 20 comes in, so let's call this 10 process 20 and 30 and 40 or whatever, right? So when P1 comes in, it's going to start searching from the very beginning. And then it looks at this. And let's say this is taken, okay? But the rest of them are available. So when P10 comes in, this is available. So I'm going to take it. So P10 comes in here. Even though I can come here, not here, but I have three choices. But first to fit means I'm going to take the first blank space or block that I can fit it in. Okay, so when 30 comes in, right? So this is done. When 30 comes in, I don't have too much choice here because I look at this table here and the only one that I can go in is 40, right? This block. So P20 comes in here and is taking 30, right? So that's all good. Now, when P30 comes in, I need a 15, right? So I have two options here. This is available and this is available. But I'm going to take this one because this is the first one I find. And why is this the first one I find? Because I'm searching from the very beginning. Okay? And that's always the case. So P30 comes in here and I'm taking it. And of course, P40, it has to wait because there's not enough bigger space here. So in order to accommodate this, I may swap out, maybe these two guys or these two guys. So this is a good example. So I may take this guy and take that guy and swap, right, into the secondary space, right? And so that this guy could go, and then maybe I'll put these together and then make it available for this to go in, okay? So so that's the first fit. Now, the best fit, so let's do another one here. So the best fit, so here is the processes here, 1, P2, P3, and I have the RAM here, right? And so let's say this is the, 10, 20, maybe 15, P4, 30 here. So after a while, I have a space here. Here's a 0. Let's say here is I have a 15. I have let's say 30 here. And then maybe I have a 50 here. And then I have another 20 here, right? So those are the available spaces. Maybe that's not the way I want to say it. Maybe I'll just do it this way. So here I have 20. Let's say I have 15, 10, 40, and then another 20. Okay. So if we're using the best fit, okay, so it's the best fit. So when 20 comes in or 10 comes in, I'm going to search from the beginning and see which one this one can fit the best. So let's say this is taken by PX. Okay, it's possible. Now these are available. Here's available. This one is available. That one's available, and this one's available. So this 10 could go in here, 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 here. So which one should this one go into? Well, I'm going to pick one that I can fit this as close as possible. So this is reasonable. This one's a little bit better because this is a little bit tighter. Not really. This one is about the same as that one. So the P1 that needs a size of 10 units, we'll take this one, okay, because this one fits here the best. Okay, so P1 goes in here with the 10. Okay. Now let me back up for a second. So when I come here, this is how much I take. Okay. P1, and now this guy right here is now available here, okay, which is a 5. Okay. Now this is taken. Now when 20 comes in, I'm going to search from here. This fits here perfectly, so I'm going to take this guy. All right. But I don't need to search anymore because it's a perfect fit. So I'll take the P2, 20, everything. So this is all not available anymore. Now when 15 comes, I have a choice between this guy and that guy, right? I can't take this one. So between the two, 15 would go in here because this one fits here better than 40. So I'm going to take P3 here, making a 15. But again, I have a space here available 5, right? So that's available. Now, so that's the best fit, okay? Now worst fit, let's start over again. So if we do the worst fit, then here's a P1, P2, P3, P4, and here's the RAM, right? And then here's the space. And let's say I have a 10 here, maybe 20 here, maybe 30 here, and let's say 40 here available, okay? And this needs maybe, this is a 15, maybe this needs only 5, maybe this is a 10, and maybe this needs a 20. So when the first one comes in, and this now is the worst fit, okay? I'm going to look for a block of space. Let's just say everything is available. This is available, this is available, that's available, this is available. So you know, you can go into any one of these. So the one that I want to pick that I can use 15 for, I can fit in any one of these 3 right here, right? But which one am I going to fit? Or am I going to choose? I'm going to choose this one, 40. Why? Because if I take here, you know, sort of like maybe I'm going to take this much space, right? 15. So P1, that's 15. What's left over here is 25 space, right? So that one's done. Now notice when P2 comes in, well, you know, that too, but anyway, so when P2 comes in, I need a 5. So I'm going to start scanning from the top. The smallest one that I see is the top one. So I'm going to take this one. So I'm going to take this one here. Nope, not yet. Rather than taking this one, because that would have been the best fit, right? What I'm going to do is I'm going to pick the worst fit. So which one is the biggest here? This is the biggest, 30, right? So I'm going to take that. So when I do, I'm going to take only 5 here. So there's a P2, making a 5. What's left over? Left over is 25. Okay, so that's done. So this is sort of not available. When the 10 comes in, let's say, let's make this not 10, but let's make it a 25, or make this guy, make these guys, make this guy 22, 23, right? So if we do that, then it'll make it obvious. So when P3 comes in, he can't go in here, right? And he can't go in here either. But notice that he could go into this one, right? Right here. These are the same, so it doesn't matter which one, but so I'm just going to take this one. But this is able to go in here only because when P2 came in, he took this space and making the rest of them available for me. Okay, so and then when the 23 comes in, right, it can also go in, not here, not there, but it can go into this one because P1 took this guy rather than this one, right? So the worst fit is pretty good because it leaves a bigger available space at the end. Does that sort of make sense, everyone? Yeah, so I take that as a yes, so sounds good. So, my question for you is, which one is the best? The worst, the best, or the first best, or the worst? Which one do you think is the best? Well, the worst fit. So the best, yeah. So there's some combination of thoughts here, but there is no really the best answer. The real answer is hybrid. Number one, okay? It uses all of them because they all have their benefits. In the beginning, we'll use the first fit because we don't need to worry about anything. That is so let me just kind of write here. So this first fit is really good because it has it's fast, right? Now the best fit is good because it leaves less waste, right? But the worst fit is good because it allows other later processes to use the remaining, right? So if you have a lot of processes that are running for a long time, maybe the worst is probably the best, right? But either way, you want to take advantage of all three of them. So in practice, your operating system will use the hybrid. But even better, it needs to be evolutionary, right? Or I should say maybe changes. To change or modify as the OS runs, right? So depending on how the user is using the programs, you want to adjust, okay? Because you don't want to just pick one and hopefully it'll work the best, because it won't. So in reality, this is what we do. Okay. All right. Hope that makes sense. Now, so what is the biggest problem with the CMA? As you kind of noticed, the biggest problem is the wasted space. Whichever you are using, there will always be some waste of space, and so that's a problem. But anyway, so let me just kind of move on. So here is the second, right? So this is the second method of managing the RAM. So here, what I like to just kind of say, let's see here, where's the do another new here. The idea here is when, so here's the process or programs or processes, right? 1, 2, 3, and they're being loaded to the RAM here. Okay. So as this is moving in, okay, I'm going to slice this, okay, cut it, slice it into the varying size. But why, right? So maybe the first one are, P1, I'll cut it into, small pieces, right? So P1A, P1B, P1C, and kind of like that. And I'll make this a 10 meg, maybe this is a 20 meg, maybe this is a 30 meg, and stuff like that, right? Why? Because in my RAM, I have 10 meg available here, right? And 20 meg available here, and 30 meg available here. So I could use, I don't have to worry too much about allocation. I can just designate this over here because I would have a table that tells me what, that's available. And for this one, I can put it right here. For this one, I can put it right here, right? So the idea of the segmentation is split the process to fit the RAM size. Okay. So that's the idea. Now, of course, it's a little complicated than what I just told you the idea, right? So we're changing, or not changing, we're kind of adjusting the processes to fit the RAM. Okay? Now, the third method, the paging. Okay? So the paging here is exactly the opposite. Well, maybe not exactly the opposite, but so here, so in terms of the paging, right? When you have the processes here, right? P1, P2, and so forth. Here's the RAM. In the segmentation, we split this to fit here. But what we're gonna then, perhaps the opposite is we'll split this, the RAM, into small pieces like that already. Then we will put these guys in here accordingly. Okay? And so we'll still have to split this, but we'll have a middle guy called the pages. And then we'll keep track of what they are and into the right fixed size. And then we'll put them in here. Okay. So we don't have to worry so much about the RAM, running out of space or, what space is available. They're all even. Okay. So but it'll be pretty compact and there is no waste. Okay. So let me go back to the diagram that I showed you at the very beginning. So here, as you can sort of see, there's a lot of space that are being, not used. Segmentation is slices of the processes, and they look pretty, well used. But here, paging is pretty intensive, right? All of them are used. So this is a further evolution. But segmentation, we split the processes, but in paging we slice mainly the RAM. Of course, we have to slice the process, but the RAM slicing is what we're beginning with. Okay, so I just want you to know the general concept of those two. But fortunately, we don't have to do a whole lot about the algorithms because the hardware takes care of this mostly. Okay, so I should say mostly. Okay? So we don't have to worry too much about it. Okay. But unlike the segmentation, we'll have to have some pages in the middle between the processes and the RAM, and we'll use different terms. The actual portion of the RAM that we use in paging, it's called a frame. And then the page refers to these portions of the processes that we keep track of, and there are many pages, and there are many more frames in the RAM. Okay, but anyway, that's the basic idea of the three major strategy for managing the RAM. Is there any question about the questions that I went over?
Could you go back to 4 real quick? I just want to make sure I got it
Let me
down.
increase the volume here a little bit. Could you say that one more time?
Can you go back to question 4 real quick? I just want to double check.
Yeah, sure. So how does the CMA work? I kind of talked about, maybe not so much here, but in the drawing, I just basically, put the processes, wherever there is a available space contiguous. But as you saw, there are different strategies even within the CMA.
Okay, thank you. Could I see number 5?
Yeah. And so the number 5 is basically finding the logical address and the physical address.
Okay, thank you. I appreciate it.
Yeah. Okay. No problem. So before we move on to the lab, let's take a quick 10-minute break, because we'll do some calculations and run some codes. So let's see here. So it is about 7:17. Let's see. Oops. Let me put on the notepad here. So, let's take a little break here. Let's be back at about 7:25. Is that okay? All right, sounds good. Okay, so let's take a break, and we'll come back and do the lab. I'm going to stop the share, and then I'm going to pause the recording. Okay, great. So let's do the lab. Let me go back to here. You guys able to see my screen okay? All right. So if you click on the memory lab, you should see this one. Let's see. So there are 6. I know that it's not the number that I usually give, but I wanted to cover all the necessary topics. So this is what you should see. I'm going to bring up my own notes. I'm going to bring this down here. And then here is so so the first question is considering the paging system, which we did not cover. So some of these questions are more of a paging and stuff like that. Okay? But anyway, if the memory reference takes 200 nanoseconds, in other words, if it takes 20 nanoseconds to access the page, right? How long does it does a page memory reference take altogether? Is the question. And so this is more of a trick question, I guess, right? So it takes 20 to access the page table and another 200 nanoseconds to get the contents in the memory, right? So if you want to look at a little diagram here, remember in the so you have a paging here. You have a page, and then this is not in RAM yet. Oh, it's sort of in the RAM, but not the actual the RAM that we think of, right? So if it takes 200 nanoseconds here, it'll take 20 nanoseconds to actually put it in, right? So it'll be 400 altogether. Anyway, so that's the first one. If the program can access the physical address from 3000040 through 420,940, like here, right? What would be the value stored in the limit register? Okay, so the limit is, I don't know if I made it in the when I went over the worksheet, but the limit is the range from the base, right? So if it starts here, 30040, and it ends here, then the limit of that process is just the difference between the two. Okay, so maybe I should just kind of clarify. So here in the RAM, if you have a process, right, PX, then here's a physical address or whatever, but here is the base, and here's the beginning, right? Here's the ending or the limit, but the limit is given in terms of a range. Okay, so if this is a 10 and this is 30, then the limit is actually 20, because we'll be just using this as a base. Okay, so you can just subtract the two and get the difference. So here's a little bit more tricky kind of questions, or a little more involved question. So if we have, let's say, start a new one. A logical address, right? So we have, let's see if I can show you logical and the physical. So if we have logical address space of 32 pages, and one page is equal to 1024 bytes. Okay. It's mapped into a physical address, right? It has a memory of 16 pages. And so the question is, how many bits are required for the logical address? So number one, question A, is number of bits do we need for the logical address? And then the question B is, how many bits are required for the physical address? So it's just pretty much the same thing, number of bits for physical address. Okay. So the bits needed for one page let me bring up the diagram here if we can follow here. So this is sort of what we have, right? So if we have a memory here, RAM, here's a logical address, and the logical side on this one, the physical side on this one. If we have 32 pages, and each page is 1024 bytes, then how many bits do you need to represent that, right? So to do that, we need 32 pages. Okay? So for the pages, 2 to the x would give you 32. This is the number of bits we need for the pages. Okay, so that'll be x is equal to 2 to the 5, or say 5, right? Because 2 to the 5 will give you 32. Let me just fact check. X is equal to 5 because 2 to the 5 gives you 32, right? But each page is 1024. So you need how many bits for that? You need bits for 2 to the something is equal to 1024. So if you by the way, let me not move too quickly here. So do you guys know? I mean, this one may be too kind of simple, but let me pause here. Do you guys know what I'm doing? Any questions? Okay, let me back up a second. I think I was going a little too fast. So what I want to do is, yes, okay. That was the before. So what I want to do is I want to figure out how many bits I need for the logical. Okay. In other words, I need bits to number of bits to refer to the number of pages, and I need bits to refer to all the bytes, right, for each page. Okay, so I need to figure out for the number of bits for the pages as well as the for each page. So in order to do that, if I have 32 pages, how many bits do I need? Let me just kind of write on the side here. If I have 1 bit, if I have 1 bit, I can get 2 combinations, right? If I have 2 bits, I can get 4 combinations, right? So if I need 32, then what do I need? Okay. So in order to figure this out, as you can see, if I do one more, if I have 3 bits, then I can have 8 combinations, right? So we can kind of go down the line. Like if I have a 4, it'll be 16. If I have a 5 bits, I can get 32 combinations. That's the reason why I said x is equal to 5. If I have 5 bits, I can address all these 32 pages. Okay. Now, if you don't want to do this way, then we need some more mathematical way to figure this out. Like for example, for this one, how many bits do I need to represent all 1024? So with the same idea, the formula is kind of like this, right? So 2 to the something is whatever you want to represent, 1024. Okay? But to solve this equation, let's see, where's my pen? You can take the log of both sides. Okay? So that becomes y times the log of 2 is equal to log of 1024. And so I bring this guy over here, becomes y is equal to log of 1024 divided by log of 2. Okay. So if you do that, you get 10. Okay. So if you have a calculator, you can kind of figure that out. So what this is saying is I need 5 bits to refer to the number of pages, and I need 10 bits to refer to the actual content. So how many bits do I need altogether? I need 15, 5 and 10. So I need altogether 15 bits. Okay. You do the same thing for the physical address, okay? Because it says let me use the green here. It says it has a 16 pages. So what I need is, 2 to the x is 16, and x turns out to be 4. Right? But we already figured out that each page was 1024 bytes. So 2 to the y is 1024. Y turned out to be 10. So here, on the physical side, I need only 14. Okay. So I hope that makes a sense to you. If not, then watch what I did, maybe when the recording is all finished. Okay, so there's a lot of calculations that's involved. We're not going to do this whole lot, but I just wanted to show you some calculations that are sometimes asked. All right. Here's one more. So let me start a new one. So here, it says the physical size of the size of logical memory, right? So here's a logical memory is 32 bits. Now, what this is saying is just giving you the bits rather than the pages and stuff like that, okay? And the size of the physical address is 30 bits. Okay? And the page, like one page, is 4 kilobytes. Okay. And the size of each page table entry is 32 bits. What's the maximum number? So this is what it's asking. What's the maximum number of bits to store to protect all the information on each of the page? So how many bits do we need altogether? That's basically what it's asking. And so in order to do this, you want to find out the size of the physical memory. And you want to find out how many pages it can hold. And then find the number of bits needed for those, how many ever pages that you just found that it needs to have. Okay. So the physical address, it told you it is 30 bits, right? So that's the actual main, the RAM or the main memory, right? So if it told you that it's using 30 bits, then you can go back to that calculations that we did. So like 2 to the x gave you whatever the size was, right? So if they told you this, how many ever bits, then it is a 2 to the 30, then it turns out to be a 1 gigabyte. Okay. And so that's actual physical size of the RAM. Right? Now, in terms of the number of pages, yeah, how many pages can it hold? Well, they just told, we just figured out that the RAM that it has is 1 gigabyte. But each frame or each portion is 4 kilobytes, right? So you divide them and see how many frames you get. Okay? And so if you do that, it turns out to be 1 gigabyte was 2 to the 30, and 4 kilobyte is 2 to the 12. Or you can do it, however many you want, whichever way you like. But it turns out to be 2 to the 18. It's easier to do it this way because you can just subtract. Okay. So the number of bits that you need for this a page is right here, right? So that's the reason why I use this way. So here, that's why I said number of bits in pages is total of 18. Okay. So how many bits do you need to protect for the protection and other information? Then you have, they told you that you had 32 bits altogether. but you're only using 18, so you could use the remaining 14 that you can use for whatever addresses that you need. You may not use all that, but you have the disposal of 32, minus the paging bits, then it leaves you whatever the remaining is, which turns out to be 14. Okay. Again, you're not going to be doing a whole lot, but I want you to at least see that there are some calculations involved because I didn't cover that in the worksheet. Okay. But let's do a little bit more of a lab that we usually do. Okay. Let me just pause here. Any questions about these 3 guys or 4 guys? Maybe you probably need to watch it again, right? Anyway, so let me get rid of this. So the next 2, number 5 and 6, is basically asking you to run the code posted on the Blackboard. Okay, so where is it? Let's go back to the Blackboard here. So I gave you 2 codes here. They're both Python programs because I didn't want you to get into trouble of running, compiling and stuff like that C in the virtual machine, because some people are still having issues, but whatever. So I gave you these 2 codes. So all you have to do is just click on one of them. So this is the base one. So if you click on it, it just takes you, shows you here, right? And the other one is the enhanced one. So you can also see here. And basically all you have to do is to look at it. Maybe this one. Okay. So here, and just run it. Okay. So you can run it in. Let's see. I think I gave you. I kind of like this one here, tutorials points. So I'm gonna open this one up. You can run it on Python or whatever. It doesn't really. I mean, Thony or PyCharm or whatever you like. So all you have to do is just grab that code. And then just paste it up here. And just run it. So let me make it a little bit bigger. So here you get to just define a random RAM size. So I'm going to say 5. Okay? I mean 10. And then if you press enter, it's going to let's see here. Organize. Grab that code one more time. Maybe I didn't grab those right. Yep. Then just run it, maybe. So if I say no, and here, yeah, there you go. So I don't know, maybe I didn't paste it right. So here I'm just saying, I'm going to pretend that my RAM is 10 whatever unit is, gigabytes or RAM, megabytes or whatever. So here I'm going to say that's 10, and you can see that it gives you some options here, and so I'm going to allocate processes to for this memory. So I'm going to say 1. So it's going to ask me, what's going on? Let's see. Let me not run it on here. I'm not sure why this is not running. run it in. Running here. And then let's see if I can run it here. So memory size of 10. I'm gonna try to allocate memory here. So I'm gonna allocate the size of maybe 5. Okay. Or maybe 7. Okay, so 7. So it allocated memory as a 0 because the whole 10 was available, right? So now there should be 3 left, right? So if I try to allocate again, and I'm going to allocate, let's say 3, right? Then it says not enough memory here. Why? Because it just that's because that's just the way the code was written, right? Because it is not running to take a particular space, but rather it takes the whole thing, right? So the next program, okay, so if you run this code, right? And I'm going to stop this one and maybe start a new one. And we paste it here. And I'll run this guy. So I'm going to save 10 here, right? And then I'm going to allocate the memory here. If I say 7, right? And then there should be 3 left, right? So if I do, let's say 2, right? It works okay, right? So this is 2 different codes that are showing you that you really have to be mindful of, where you put your memory location, the process in which part of the memory in the RAM. So basically, all I want you to do is run the code and play with it, and you can also deallocate the memory too. But see that there is a little bit of an improvement of the second code. So basically, this is both of them are using the first fit method. And what is wrong with this first one? It doesn't split the remaining portion of the RAM, and so there's it doesn't work too well, right? But if you run the second one, it's still using the first fit method, but it splits the remaining block into a smaller size, so that it allows you to use the remaining processes. Okay. So anyway, that's a quick demo on how to do this 2 codes. So make sure you grab the 2 codes here and try to run it on here in the tutorials point. But if that doesn't work, then just use whatever platform you use. You may work on Program Is. Let's give it a quick try on Program Is. So I go there. Oops. And if you run it, say 10, yeah, it works here. So you can use any of the online programs or installed programs. Okay. Any questions about these 2 programs that I ran? You guys doing okay? Okay. Sounds good. I just not sure. Yeah, that's it. But that's pretty much it. So I wanted to show you. This is not a coding class, so I didn't want to spend a lot of time, going over like whatever. So if you are interested, you can look over the codes and trying to figure things out. But this is a really basic program, and so your actual RAM code they use for the Windows 11 or Linux or whatever is much more complicated and diverse. But I wanted you to kind of give it a try. All right, sounds good. Any questions about what we covered today? All right, well, let's kind of wrap it up here. So, again, next week is a spring break. So we don't have a class next week. So, we'll come back on week number 10, 2 weeks from today, March. It should be March 20, right? Yeah, so I should update these dates, but anyway, so next Wednesday, 13/20. Yeah, so we'll be back. So I'll see you on 3/20, Wednesday. All right, sounds good. If there's no question, have a good rest of the day, evening, and I'll have a good break. I'll see you when we come back. I'll stop the recording.